Hi. Yeah. Hi. Hello, everybody. Thank you for joining us today for the Kaapi with Curiosity lecture by Professor Frank Den Hollander, How Networks Shape Our Lives. So, Kaapi with Curiosity is a lecture series that is aimed at increasing the curiosity of the public towards various aspects of science, which is organized by the International Center for Theoretical Sciences in association with the Jawaharlal Nehru Planetarium. Before we move on with the program, I'll give you a brief introduction about the International Center for Theoretical Sciences. We are so International Center for Theoretical Sciences is a center that is a multi and interdisciplinary center with three main goals. So one is research. So ICTS contributes to research excellence in theoretical sciences with its high quality faculty together with a large floating population comprising of visitors, postdoctoral fellows and students. And the second is programs. So we try to bring together researchers from all over the world under one roof to work together to solve the most challenging questions posed by nature. And the third is outreach. So we attempt to take the science that we do to the civil society. Kaapi with Curiosity lecture series falls under outreach. So other than Kaapi with Curiosity lectures, we have a lot of other outreach programs. And even in academics and programs, there is a lot of ways in which you can be a part of ICTS. So all this will be advertised in all of our social media. So if you don't already, please do follow us on our social media by scanning the QR code. So I now welcome Dr. B.R. Guruprasad, the director of JNP, for the welcome address.
Respected Professor Hollander and other visiting faculties, Professor Shivatreya, and ladies and gentlemen, invitees, and good afternoon to all of you, and welcome to yet another edition of Kaapi with Curiosity talk. As she told just now, this is a joint program of JNP, Jawaharlal Nehru Planetarium, Bangalore, with ICTS, and these talks which are aimed at general public and students as well. Okay, they are one of the most popular programs of ours, and today we are honored here to have Professor Frank Den Hollander from University of Leiden, Netherlands, and we are indeed honored, sir, by your presence. Thanks for accepting this. On behalf of JNP and ICTS, I welcome you, sir. And the topic is very interesting, how network shapes our lives. Okay, when I saw this topic, really, I remembered Marshall McLuhan's Global Village. That concept long back when communication satellites came into picture, or even before that, he told about this. Anyway, I don't want to preempt anything else. Once again, I welcome Professor Hollander, Professor Shivatreya, and all others, all of you, on behalf of JNP. And now, Sharanya, mic is yours. Announce, please.
Thank you, sir. I request Professor Shivatreya from ICTS to introduce the speaker.
Good evening. It's with great pleasure that I introduce Professor Frank Hollander, the distinguished scholar whose work has profoundly shaped probability theory across time. His research influences probability, statistical physics, ergodic theory, population genetics, and complex networks, which is the topic today. Frank received his PhD in 1985 at Leiden University. Over the years, he has held several positions at leading Dutch universities and is currently a professor at Leiden since 2005. His scholarly record is remarkable, over 200 papers, 3 monographs, and significant mentorship of over 30 PhD students and equal number of postdocs. Frank has also contributed severely to services, community services. He has shaped European research as its scientific director of Urandum, and also served as a decade as chair of the Advisory Council for Natural and Technical Sciences of the Royal Netherlands Academy of Sciences, where he was elected a member in 2005. It's quite fascinating. In recognition of his career-long commitment to improve mathematics, both nationally and internationally, he was appointed Knight in the Order of the Dutch Lion in 2016. I hope I got that right in the order. I have known Frank since 1998 when I was a postdoc at the Fields Institute in Toronto. So I recall one day, I think in early February, it had snowed so much, the temperature was minus 23 degrees centigrade. And I had never seen that mark on the thermometer. So I ventured out to experience the weather, and I walked to my office. I climbed up this building. Fields is an open institute with a sort of a middle staircase, and the building was empty, except in one office, Frank was working away on his computer. I think that gave me a new definition of what a hardworking person is. I think it's truly inspiring. And I learned something more about Frank. He likes temperatures below 18 degrees centigrade. So I think so. And Frank continues the same energy even today. He's well known for his warmth, energy, and very, very positive and constructive attitude. And last but not least, his tremendous personal commitment to colleagues. I think so. He's also a senior associate faculty at ICTS. You saw those three verticals, or not here, the previous slide had. He contributes to the research by many research project collaborations. He also organizes a program right now running in ICTS on networks. And today he'll deliver a talk on how networks shape our lives, contributing to ICTS's third vertical of outreach. I warmly welcome Frank. It's a small goodie bag for you.
Oh,
Not all.
thank you very much for the kind words, and thank you for the invitation to speak here. Thank you all for coming. It is so much joy that I can stand here and tell you about how networks shape our lives, and they do. They do in many different ways, and they also do so in ways that we often do not even think about anymore because we think it is all normal. Right. And my plan is to take you on a brief tour of networks and various properties of networks, good things about networks, bad things about networks, and to tell you and to show you how important they really are today. Now, the beginning of my story is only half a century ago, there were very few networks around, and the world seemed very large. Everything in the world was far away, difficult to reach. We didn't know what was happening. And I remember when I was a boy, my mother had a friend who was living on the west coast of the United States, not far from Seattle, and they wanted to call each other twice a year. But calling them was a very difficult enterprise. So my mother had to call the local phone company and say, I would like to talk maybe 2 days from now with my friend, and she's living near Seattle. Can you arrange for a phone connection? And then this had to be organized. And then after a while, the message came back, yes, we will call you up on Sunday morning, and she will be waiting on Sunday evening, and we make this connection. And then they had to sit both by the phone, and the local phone companies would call them at home, and then they could talk to each other. And it was very expensive to do so. We knew about things happening in the world. I grew up in a small country in Europe, the Netherlands. I knew about India. I knew about China and Japan, but I didn't know much. There wasn't much news coming. So if something very big happened, we would learn about it maybe a week after. And so the world was really very big at that time. Now, life is completely different. And the reason it is different because we have very many networks through which we communicate, through which we are interconnected. For instance, this difficult phone call is no longer a problem. Siva can pick his phone, he can dial a number in the US, and in 20 seconds he will have his friends on the phone. Unbelievable. And this is because of the satellite networks that we have that allow us to do all these connections. Nowadays, news travels viral. If something happens in South America, we will know it within a few hours if it's an important piece of news. So the world today has really become very small in some sense, and it is because we are very much interconnected. Now, in the next few slides, I want to talk with you about 7 examples of important networks that play a role in the life of most of us. And I want to tell you about briefly what they're doing. You will recognize most of them and why they're important, what are some important facts related to these particular types of networks, and what is exciting about them. Now, the first network that you all know is Facebook. And Facebook is a friendship network. It's a communication network. It's a network through which people share their experiences. They want to share it with other people. They want to share pictures, maybe share some happy events about a child being born or some great event happening in the family. And it is all about being able to feel connected to other people. And the Facebook is enormous. It's a very, very big network. It's not a network that I could draw here on a piece of paper. It's too big to do that, but it's there and it plays an important role in our lives. And this is the first type of network that I would like to present, and you all know it. And this is all about staying connected. People want to stay connected and they find different ways of doing so. And Facebook is one particular such social network through which people communicate. The World Wide Web. The World Wide Web is basically a collection of web pages that contain information and that are linked to each other. And the World Wide Web is big. There are billions of web pages. When you go on to the Google search, you are looking for something, and it is through this network that you will find the information. There is a famous algorithm, Google PageRank algorithm, that you are, without you knowing it, using it when you look for something. Because what it does, this gives all the nodes in the network a weight of importance, and when you ask for a certain piece of information, it will put on the top of your list the web page that has the biggest importance in the question that you are asking for. So the World Wide Web is not only a network that is there for us to use, it has also a nice algorithms through which you can easily find information in this network. And this network, as I said, is very big and it's also very dynamic. It's changing, every month about 10% of the World Wide Web is changing, has changed into something else. And if you would look at people's Facebook pages, you will also see that things are changing. So these networks are not only often very big, they're also very dynamic. They move in time, they change in time, because we want to use them. Here is a local transportation network. This is a network with the railroad lines in my country. And my country is small, and I can still draw a picture of all the railroad lines that there are there. And these are the main train lines. And for instance, you see that on the western part of the country, where the majority of the people live, the railroad system is much more intense than on the eastern part and the northern part. And this is a picture where this is an example of a transportation network. So trains we use to go from one place to another. And because this is a local network, I can still show a picture of this. In the city of Utrecht, Utrecht is in the center of the country here. There is the main center of the railroad company in the Netherlands. And 1 out of every 3 trains is either on its way to Utrecht or coming for Utrecht. And in this center, they control how trains are going around. And since the network is not so big, a few hundred stations, you can still look at it. You can still draw a picture of it. Whereas I could not draw a picture of the World Wide Web because it has billions of web pages and I cannot even visualize this. So even visualization of a network can be very different for different types of networks. And in Utrecht, they regulate things. If something goes wrong around the city of The Hague, it will have an effect for all the traffic that has to go through the north, Groningen. And so the center in Utrecht has to be careful and monitor how this network is supposed to operate. And if there's a disturbance or a disruption somewhere, they have to start to think about what to do in order to make people go where they want to go anyway. And sometimes they tell people to take another route through the place where they want to do this. So the fact that the network looks like this is not a coincidence, it's sort of optimized. It allows for alternative routes if there is a disruption. And if you build a network, you have to also think about these things. Like a network has to operate well, and it also has to operate well in times of trouble. So there are many things you have to worry about when you build and operate a network. Here's a much bigger transportation network. It's the network of all international plane routes. And this can already not be nicely drawn on a piece of paper anymore because there are thousands of airports in the world. And when you fly, it's not like you go to Bangalore airport and just hop on a plane. No, a lot has happened before you board the plane. You have to buy a ticket, right? And it says you're going to leave at time 10:10. Oh, okay, so there's an idea. There has been a plan. Suppose you fly to New York, then New York has to know that the plane from Bangalore is arriving approximately 10 hours later. So you have to plan things ahead. And when you sit in the plane, you have to wait before you leave. And the captain of the plane says, we don't have any permission yet to leave because in New York they're not ready to receive us. So for you to fly is an enormous preparation, and you have to have the permission of the airport where you're going to for you to be able to leave. And by experience, they know the flight routes more or less how much it takes, so they can do good expectations of when your plane is going to arrive. And that's the challenge that this flight captain stands for. Now, we know that certain flight routes get disrupted. We can no longer safely fly over the Middle East at this moment of time. It's a bit better now, but a few weeks it was very impossible. So what do you do? As an airline company, you have to think of an alternative solution. You have to go and take a different route. But it's not like you're saying, okay, let's just do that. That requires an enormous preparation. You have to have permissions to fly over airspace. And so this is a global transportation network where you really require all the airports to be in touch with each other and give each other permission for these flights to leave and to arrive. And if something in between happens, something has to be solved. And so if you want to make this network work well, you have to communicate, you have to optimize, you have to make sure that things are happening. Safety is very important. You don't leave and fly over a route when you're not safe. And if it's not safe, you have to think of something else. So there are many issues here about international plane routes that require lots of preparations, and sometimes the preparations are done weeks ahead or months ahead. And when the network is really big, you're going to have more problem than dealing with this little local train network in the Netherlands, which is easier to handle, and yet also requires lots of preparation. Here is a picture of a banking network. The dots are banks, and edges between these banks represent the fact that these banks are trading with each other. And there are some very important banks. We call them hubs in the network, and they are trading with many other financial institutions. And it's a big, complicated cloud of banks trading with each other. And this trading of the banks is very important. If you put your credit card into a machine and you want to pay, then it's not the case that this is just done on the spot. Some data travel to somewhere. They check whether this credit card is still valuable, valid. Maybe you blocked it and then you cannot pay. If you try to pay a very big amount of money, then maybe there's a check and say, no, you cannot pay that amount of money. You can maybe pay $50, but if you want to pay something that is 12 million, you're going to say, you cannot do that with your credit card. So there is communication and safety and security about these things, and financial institutions do have to do that in order to make your financial network work. And we all take it for granted that when you stick in your credit card, you want to be able to pay. And you want to take home the product that you want to buy. And we think that's normal, but behind this whole system is an enormous control of financial networks that you need to make sure that payments can be done, payments are safe, and the network is not disrupted. And when there is a financial crisis, things really change. I have a colleague at my university who has studied how the structure of financial networks change during a financial crisis, and he clearly saw that during the financial crisis that we had about 15 years ago, the banking network looked different from what it looks today. And so we very much rely on our being able to pay things in our financial transactions, and we would like to make this work, and there's a whole world behind it that is part of the world of financial networks. Another example of networks apart from the social networks and the information networks and the transportation networks that I have talked about so far. Energy networks. Wow, that's very important. There's oil, there's gas, there's electricity. We have windmills to create electricity. We want to put batteries at home to store electricity. France has a lot of nuclear plants. And all these energy sources are connected to each other in a huge energy network. And we, again, find it normal that we plug our charger of our mobile phone into the network, and we expect that we are going to be able to get this electricity, but the fact that it's there is not easy. And one of the complications is that the demand varies over the day. The different forms of energy have to be treated differently. Oil you can save in a pot, but electricity, well, you have to save it in a battery, and that's a more complicated process. Nuclear energy has to be in a nuclear plant. It's not that you put it in a pot, screw the top on, and put it on your shelf and say, I'll get the nuclear energy whenever I want. I mean, these things are complicated to deal with. And nowadays we rely on many different energy sources, and they're all coupled. So that if there's very little sun, then we use a bit more of the windmill energy. And if there's little wind and there's no sun, then maybe we revert to what we have put into batteries. And to make this whole thing work is a major problem. The energy companies have to put enormous effort into making this network workable, efficient, stable. You don't want there to be a blackout where at some point you come home and you say there's no light, there's not anything anymore, there's been a big problem and I don't have anything. So the energy companies will do everything they can to avoid that. And every now and then there is a blackout and we have to live with that. But what is behind the technology of making this work is enormous. So this is another example of a network that plays a major role in our world. This is the last network that I want to talk about, and that is a neurological network, the human brain. The human brain is the most complicated network that we have. We don't quite understand it. When we build our computers and artificial intelligence, we try to sort of imitate a bit what the human brain is doing, but it is very difficult to understand. In the old days, we couldn't study the brain because you cannot open somebody's skull because the person will die and you cannot measure the brain. Now, with electrodes, we can do measurements on the brain and learn a lot about the brain, but it's very difficult to understand how the brain works. For instance, memory. You store memory and you retrieve memory. And the way the memory is retrieved is sometimes very strange. Sometimes I come home and I have a friend who asks me, and how was it last night? I said, oh, what did I do last night? I went to this theater play. Yeah, I said, yeah, it was a very nice theater play. I really enjoyed it. But I had to think of what I was doing last night, and it can take me maybe 20, 30, 40 seconds to find this. But there are also other pieces of memory that are at the tip of your finger. They ask you, what was the name of the girl sitting next to you in primary school? And you say, oh, that was Charlotte. And I haven't thought about Charlotte for 50 years, but when a person asks me, Charlotte is there immediately. Now, why is that? Why can I bring back Charlotte immediately, and can I not bring back so easily what I did last night? So the brain has various layers and ways of storage, and the way it's doing this is still somewhat of a mystery, even though we're rapidly beginning to learn how that is helping us. So why can we reason? How is it that the brain can reason? Well, they're neurons, and they're synapses, and there are billions of them. But how is that working? Why is it that when I give you a picture, a very big picture, that you could say, I see Siva sitting in the corner. So I'm able to ignore most of the picture and I see Siva sitting in the right corner. So my brain is capable of doing a recognition in which I recognize a person and I'm able to say, I don't want to look at the rest. How the brain does that is, even today, to a large extent, a mystery. Now, I've given you 7 examples of these networks, and they have various different aspects. Each network has its own particular peculiarities and style. But I can also ask the questions, what do they actually have in common, all these networks? Yes, they're very different in certain aspects, but are they also similar in other aspects? And the answer to this is yes. Many networks, even though they play different roles, they have important things in common. And the fact that they have important things in common is exactly why we know how to handle them. We do not have to, for every new network, come up with completely new ideas, because networks have things in common. For instance, it is typically the case that you can quickly navigate from one spot in the network to another. If you're on this World Wide Web, it's billions of web pages, but the Google page rank allows you to very quickly spot what you are looking for. It doesn't always work, but very often you can travel between there. In an airplane network, it takes me a day to go from my country to Australia. Only a day. And so I can easily find a route through these enormous networks of airline connections, to go from pretty much any place in the world to any other place in the world. And I don't have to take a very complicated route and change trains 32 times. So that's remarkable. I can travel easily within this network. It is also the case that many of these networks, what you see locally does not depend on the size of the network. I remember when we went into COVID and we had to all communicate from home, there were people asking, oh, now the entire net is going to collapse and we're not going to be able to do this if everybody in the Netherlands sits and wants to have a Zoom meeting. No problem. And if you would scale the World Wide Web up by a factor 100, it would still work. So there is something about the network that you say, if I'm in the network and I sit somewhere here, I see something, and if I sit somewhere else, it more or less looks the same. Yes, there are remote spots in the world where I will see less, but basically these networks have a kind of homogeneity, and no matter where you are, they look a bit alike. And what is also common in many networks is there are what is called hubs. So nodes that are connected to many other nodes in the network. And almost all of the networks have this feature. Your brain has it. There are certain spots that are having connected with many synapses, and you are using them as sort of control centers. If you travel, if you take an energy network, you will see that there are certain spots where a lot of energy is being stored and created, and they play a role in also transmitting energy. For instance, in Europe, all the networks in the various countries are communicating with each other. There are moments when England says, we have more than enough energy, let's send it to the Netherlands because they're short of it. And there are hubs through which this is actually happening. So these hubs are very important for how life works, for the efficiency of networks. Networks tend to mostly be large. sometimes millions and even billions of nodes. They tend to be very dynamic. It's not that they are the same for the next 20 years. They evolve, they grow, they change. And it's this dynamics that is also something very important for the way networks work and for the way we can control them. Many networks are overloaded. Well, why? If you build a network, you'd like it to be used to maximum capacity. It would be bad if you build a network and say we're only using 1% of it. So many networks are pushed to the rim of being able to have many hard-working parts and everything. Networks are also vulnerable. If something goes wrong, other parts in the network may also go wrong, and you have to be very careful to make sure that the networks are safe and can take a blow. So the networks have to be built in such a way that if 10% of the network has trouble, the rest of the network can still function. And this has to be done in a clever way, because there's not somebody looking at and then saying, okay, something there wrong now, let's have more web pages there. It doesn't work like that. You cannot control a network other than through what people are called local protocols on how phone messages are sent through a network. And so the vulnerability is very important that you address this. Otherwise, most networks would not so easily work. You'd like networks to be working efficiently, and you like them to work very well, because if you plug your charger of your mobile phone, you want it to charge your mobile phone. So better make sure that that happens, or otherwise you're going to become unhappy. Not everything about networks is positive and upbeat. There are also parts where you say, maybe we have to worry about a number of things. For instance, privacy. If your data go into a database, are they safe? So if you go to a hospital and the hospital has medical information about you, maybe you don't want other people to know about your medical information. Some people are fine with that. Other people say, no, I don't like other people to know that I'm ill. Safety. Networks under attack every day. At my university, there are 750 attacks happening every day, and they're able to wield them off. But it's amazing. So you have to make sure that your network is safe and that hackers cannot destroy it. Now, to make a network safe, you can seal it off. But that's not what we want to do either, because we also want openness. If you have data, you would like to have people to access to this data. Papers are nice when they are open access. Everybody in the world can see what is written in these papers. And so also accessibility and openness is very important, but these three things together are not so easy to do, all of them, and you have to worry about reliability and protect networks against problematic points. So not always, there are wonderful things about networks, and we can say we're happy that in the last 50 years we've developed these wonderful networks so that we can fly everywhere, and we can ring up everybody where we can get energy from anywhere, but it comes with a price. And often we don't think about that, and there are other people who make sure that the network will work for you. Now, networks also sometimes have surprises. Things that you would not expect to happen. And I want to talk about two of these surprises. And in the two examples that I'm going to give you, and then after that I will round off, I'm going to use a little bit of mathematics, because I also want to show you a little bit of mathematics. I'm a mathematician. I love mathematics. And mathematicians think about networks. Physicists think about networks. Chemists think about networks. Social scientists think about networks. And also mathematicians think about networks. So bear with me. It's not going to be very complicated, but a little mathematics we're going to do. The first surprise is something that is called the friendship paradox. And the friendship paradox says, and it was discovered by a social scientist in 1991, he said, on average, your friends have more friends than you do. You say, well, that's strange. Well, what does that mean? I'm as much part of the network as anybody else, so how can it be that on average my friends have more friends than I have? Well, it is true. And let me tell you what he exactly meant. Here I'm giving you a mathematical picture of a network. There are nodes and the links between the networks. And this network is a mathematical network. It could represent any of the networks that I was talking about before. But as a mathematician, we'd like to look at this picture and say, I like that. And what you're going to do, you're going to pick a node and you're going to compute a number. And this number is the difference between the number of links that come out of that node minus the number of links that come out of all the neighboring nodes averaged over these neighbors. So this is a little formula that says the degree of node I, you subtract it from the sum of all the degrees of your friends divided by how many friends you have. And so this is the average degree of your friends, and this is your degree. And the friendship paradox says if you take all these numbers for all the vertices, sum them up and divide by how many there are, so n is the number of vertices, nodes in the network, you always get a non-negative number. There is no network in the world for which this would become a negative number. So, well, why is that? If it can be positive, why can it be not negative? No, it's always non-negative, and you can prove that this is the case. I'm not going to give you the proof, but it is a fact. So the friendship paradox is not a paradox, it's actually a fact. But it sounds so paradoxical that you say, how can it be that my friends on average have more friends than I do? And a mathematician can prove this for you. And the fact that there is this bias that you say your friends always on average have more than you is useful. Here's an example why. Suppose I have one vaccine. You are a group, social group, and I know that there is an illness in the group, and I would like to help by giving a vaccine to one of you. Now, I could do this in two different ways. I could close my eyes, pick randomly, choose one of you, and then give this vaccine to you and say, do vaccinate yourself so that you will be less contagious in the rest of the group. This friendship paradox says, there's a better way. What I do is I close my eyes, I give the vaccine to a person, and I tell the person, do not vaccinate yourself, close your eyes, pick one of your friends, give the vaccine to your friends, and ask the friend to vaccinate himself. If I do that two-step procedure, I will reach, on average, a person who has more friends than I have, and therefore it will be a better spent vaccine in this way. So the friendship paradox, which is purely a mathematical network thing, has a useful application when you start thinking about vaccination strategies. Do not give it just to anybody, but give it to anybody and then ask to give it to a friend. So that's a wonderful thing, a nice application of a very simple principle. The second example I will give, and then I will round up, is polarization. We see this happening in many countries now, and in the United States in particular. You see that people who are in a social network, they have different opinions, and there is a tendency to say, oh, you don't share my opinion, I don't want to be friends with you anymore, we stop communicating, and because I don't like to communicate with people who have a different opinion. And if you have that mechanism, what you will see is that the whole society will fall apart into two groups with opposing opinions that no longer have any friendship ties between them, and they will stop talking to each other, and they will certainly not try to convince each other maybe to change your opinion, because you talk to your friends and then you say, yeah, well, I understand why you have this opinion, but look, I view it like this, and maybe you would say, yeah, well, yeah, maybe I should reconsider a bit. So by talking, we build consensus, and if we stop talking to each other, there is polarization. And you can start with a very simple network, and then you can do two things. You could say, when you're connected, maybe talk to each other and transmit your opinion, or you could with a certain probability, you can do that with a certain probability P, and then with the remaining probability you could say, I am going to stop my friendship, I'm going to send my friendship to somebody else, I want to make a link to somebody who has my opinion, right? And you can show that depending on what this tendency to do one or the other is, that you may end up with a group of people who all happily talk to each other and continue to agree with each other, or you might end up with a situation where half of the group is talking only to itself and the other half of the group is only talking to itself, and there's complete polarization and there's a rift between these things. So this kind of phenomenon is what people, influencers study. So it plays a role in political strategies. So two examples, very simple, a little mathematical, about what networks can do, sometimes really surprising things that you would have not thought of. So I'm about to wrap up, and a few things I want to say that are very general. So networks have been around abundantly for the past 50 years. Of course, we had travel routes in China, Silk Route, universities formed networks that are much older, but the networks of today have really changed our lives. And networks are important, and network research is done worldwide. Every country has people at university or scientific centers, also at ICTS, working on big questions about network safety, security, vulnerability, effectiveness, optimality, control, and everything to see how we could perform best with networks. And in the Netherlands, we have a program running for 10 years now, which was funded by our Ministry of Education, Culture and Science, that is all about trying to understand networks, do research on networks, and involve the mathematicians, the computer scientists, the physicists, the social scientists, the biologists, a big vision towards networks. And what these researchers try to do is they try to analyze, optimize, control, protect networks. These are all interesting facets of what is happening. And it's challenging because these networks are changing over time. On the networks, things are happening. People are traveling, people are sending messages. So it's a very dynamic environment. And you want to be able to understand what is happening. And so for vaccination or polarization or consensus issues, you really want to understand how you can make sense out of this dynamic world. And networks have many different facets. And I claim that for the next 50 years, we're going to be really working hard on the networks, and AI is going to help you. Thank you.
We're open for questions now. So,
thank you, Professor, for your enlightening lecture. I have a couple of questions. Number one is with reference to the, the population where there is a polarization.
Yeah.
So, is it governed by the binomial distribution, or is there any other distribution that is governing?
The binomial distribution does pop up in some situations, but there are also many more complex situations where it's not binomial or that simple, where it's really this polarization is the resultant of many things trying to compete with each other that you could not capture with very simple tools. In fact, to describe polarization is one of the hard things to do. There are many things that we do not really know how to do well. We can simulate with big computers lots of things,
Okay.
and we can do all sorts of heuristic thinking, but to make things precise is hard. So polarization is difficult, and it's complex, and there are many different tools somehow that you need. So it's not so simple as one might think or hope or whatever.
Okay.
It's a big challenge.
I see.
Yeah.
Okay. And then second question is with reference to the current progresses as regards the quantum computation and all those things. So is there any quantum entanglement being researched for the instant communication or something like that? Is there any current?
Yes, of course, quantum computing is a very important fact. I mean, our current computers use networks, and if you want to use quantum computers, you also build networks, and then you have to start asking quantum questions about networks, and that's being done. That's a big area now. It is experimentally hard to build a quantum computer. We now have a computer, I think the biggest one is now 30 bits or something, and there's a lot of investment, and again, questions of networks in the world of quantum are very important and very relevant. So network research is also working in the quantum world. I am not working in this particular area, but I know it's very important. And I think if the quantum computer will one day be there, and we would all hope that that will be the case, it's going to be a major breakthrough. Yet there will still be many things that also the quantum computer cannot do. So many of people seem to think, oh, once you have the quantum computer, everything can be solved. No, there are things that even a quantum computer cannot do. Okay.
Thank you.
Okay.
Hi. So, okay, thanks for the interesting talk. I had two questions.
Please.
One is the friendship paradox that you said. Is that the reason that you get polarization, or there is some connection between the two paradox? And the second question is, when you said that you always find hubs in a network, why is that?
So let me start with your second question, which is easier to answer. We think that we get hubs in a network because networks grow. It's not that the network is given to you now. An airplane network started very small and it's growing. And the reason why we think hubs occur is because when a network grows and a new node comes in, it is simply more likely that this node connects itself to a node that already has very many links. If you are entering a social network, you will probably first get to know the person who already has many links in the network, who already has many friends. You will probably not, for the first time, meet a person who is all isolated. So you will build your friendships more likely with people who are already having many friends. And this is a principle. Sometimes we call it the rich are getting richer and the poor are getting poorer. But this is called preferential attachment. And because networks grow, and they are today what they are because they started small and they've been growing, and this growing mechanism often uses preferential attachment as a kind of growing mechanism. That's why these hubs are there. So this is one very plausible and very nice and very interesting interpretation of why hubs are there. I mean, in an energy network, you build the hubs because you need to have places where you can switch the energy channels. But in social networks, nobody tells you who to become friend with, and it works like this. The other question is, that you said your first question, polarization has nothing to do with the friendship paradox. The friendship paradox is a bias that says you are simply more likely to be connected to people who have many friends because they have many friends and you're more likely to be one of them. Polarization is more the opposite. It's more like saying, I don't want to be friends with you. I don't want to talk to the people who disagree with me. I only want to talk to the people that I agree with. And that's a different phenomenon, but also a very relevant phenomenon because we see it all around us, much more today than 10 years ago. Polarization is a problem and a real worry that we don't talk to each other anymore.
Thank you.
These networks are developed by human civilization. The nature has already networks. We have light, we have gravitational waves. Without light, I can't see you. I can't see anything.
Yeah.
So it has already networked the entire universe, which includes all planets, all cosmos, the entire galaxies.
Yeah.
And within that, we humans are networked.
Yeah.
But we have the anthropogenic attitude is we have emotions which have no value for universal design.
Yes.
So we can is it possible to redesign the human civilization based on the network of universe? Because we can't be polarized. The speed of light is speed of light. We can't have an opinion.
No, that's a beautiful question. I think what is happening is that there are networks that are technological, and it's not about opinion or not about human behavior. So the World Wide Web is built in a certain way. The energy networks are built in a certain way. The airplane networks. But once you go to social networks, it's a different story. So, because on these networks, all sorts of things are happening. So they put an influencer in the network, and it says, the influencer starts to talk to everybody and says, you should buy my product because it's so beautiful, and look at me, I've used this project. So there is human behavior put onto a network that is otherwise simple. And it is when you start to have these various different features that it becomes very, very difficult. Social networks are much harder to model because we don't have yet a good understanding of human behavior. I mean, there's an area called game theory. And then, so people do things based on something, and maybe they take an irrational decision because they believe in something else. And then you say, well, I need to understand this to understand what the social network is doing. The other point you say is there is the Internet of Things. At some point, we're going to connect everything to each other. And maybe we'll be able to connect to the backside of the moon. And then all sorts of other things are going to happen. And I don't know, we have to dream about what can happen. It's also dangerous. When you connect everything, things can go pretty wrong. So there's a lot to discover. And that's also one of the reasons why I said in the next 50 years, we'll really be still very much busy with that. It's not a thing of today. It's still also a thing of the future.
Hi, Professor. Thank you for the wonderful talk. I was wondering, what's your opinion on studying networks from the point of view of higher order interactions, not just pairwise interactions, but
Very nice. There is a notion called multigraph and of hypergraph, I should say hypergraph, where you're not just talking about two nodes being connected, but you could say, okay, two nodes are connected, several nodes, but there is also some sort of commonality between three nodes. Maybe I put a triangle there on top of it. So there are many higher order things that are also very relevant. We call it hypergraphs rather than graphs. They are heavily studied. They are very interesting. They exhibit lots of new phenomena. The examples I've been giving you are more sort of the more easy type. They're also quite challenging. So there are things on hypergraphs that we have to study with. And you see people in mathematics and in computer science very much hard at work. So you're right, there are multiple ways in which we could be connected, and that's relevant for many questions that we want to ask.
I think there was a paper recently where, I forget, I think Thilo Gross, if I'm not mistaken, on Archive I saw, where they said that pairwise connection is enough. So
I don't think so. I think there are higher order connections that can really do something. And I believe that in the brain, probably with memory, there's a hierarchical way of ordering. The fact that you can remember certain things easily and other things not, probably is because it's stored in a different way. And this probably has to do with higher order interactions. And there are certain things that you could not capture by only looking at pairwise connections. Can you put one? Yeah.
I had a doubt in the friendship paradox. So
Yeah.
you said my friends will have more friends than me.
Yeah, on average.
But even my friend is my friend. So in his perspective, I should have more friends.
Yeah, that's why it is a paradox. When you first think, you say that's not possible. It sounds like saying we are all on average taller than our average. Well, that's not possible. So it sounds paradoxical. But the reason is, in very simple words, but there is a hard proof for this. In a network, you are more likely to be connected to a person who has many friends. So you already have a friend that has many friends. And that fact gives a bias. In the network, there will always be nodes for which the friendship bias is negative. You say, I have more friends than my neighbors. But there are also nodes that are such that all their friends have more neighbors. And the statement is, if you average this out, it doesn't vanish. You still have a positive result. And you can prove, very simple but beautiful proof, there is no network in the world for which this bias would be negative. And the only way in which it can be zero is when the entire network is homogeneous and everybody has the same number of degrees. Only in that case, the friendship paradox disappears, but in any other network, it will be there. And I challenge you to go home, draw any network you like, do the computation, and you will find that I'm correct.
So it's like statistical, not...
Yes, it is. There is a bias. You're more likely to be connected to a person who has many friends. And that means you have a friend who has many friends. And that's why this is happening on average, even when you average over the entire network.
Thank you.
Clear? Yeah? Okay.
Thank you. Thanks for the talk. It was very interesting. So
Yeah.
I want to ask, is there any qualitative differences between graphs that change or grow over time, like graphs where you add nodes and edges, or graphs where the edge set just changes? Or can you always model a growing graph by adding empty points at the beginning and just filling it up?
You have graphs that are dynamic because they grow. More vertices are coming in and connecting to the graph in certain ways that you could choose to model some phenomenon. And sorry, you also have graphs where the number of vertices stays the same, but the graph is just changing in the sense that maybe an edge simply says, I'm switching off, or I'm going to relocate to somewhere else. So in this polarization phenomena, if you and I have a friendship, but you would disagree with what I think, you might say, I don't want to be your friends anymore. I develop a friendship with another person. So that is a form of dynamics in the graph. There are many different forms of dynamics that you could think of, and actually dynamic graphs and processes on dynamic graphs are difficult to study.
So there are like non-trivial differences in the two cases. You can't just reduce one to the other.
No, you cannot sort of simply translate everything back to a simpler situation. They're all new classes of problems that you have to face again and handle.
Thanks.
You're welcome.
Any other questions?
So I understand that, I mean, it's very nice that one can compute these various very useful mathematical properties. And when you're talking about, like, say, public health efforts like vaccination, we find that at a mathematical level, we can come up with good arguments for when something works better.
Yeah.
In practice, how often does this happen in the real world? Like, are governments and public health officials actually talking to mathematicians?
Yeah. Very, very good. What happens is that the true behavior of an epidemic is complicated because people start to move around. People make rational decisions or irrational decisions. So it's hard to really model this. So the role of maybe a mathematician is to say, okay, I have a few simple marker models. They're not going to explain your reality, but knowing what they do will be helpful for you to perhaps do a little bit better in the complicated models that, as a mathematician, we can't really deal with because we don't know everything that is happening in these networks. What you see, so epidemiology is a very well developed field. Since the 50s, people have been working hard, and during the COVID crisis, there was a lot of people involved from various different disciplines, and we're beginning to include more and more realistic models. And so there is also a kind of robustness that you say the models have lots of things in common, and so if I understand a certain property, it should also apply to your problem, even though it's not exactly what I'm doing. There's universality in the world, and this is how we climb up. But to really deal with very volatile and very difficult situation is very hard, and we use computers to do that, and we are using AI, and we're going to use much more to say, don't do this, do that. It's interesting, yeah. But you're right, reality is often much more complicated than what a mathematician or a computer scientist or even a social scientist can do. Okay?
Okay. Do we have any more questions? So, okay. I thank Professor Franklin Hollander for such an event. So, I request you to keep yourself occupied for a little while. Our coffee is a little late today. We'll let you know when the coffee is served. Thanks a lot.